Hi everyone, this is Mayur M from team Moonquake Alert System, that is 301. Let's get started with our presentation. Next. Yeah. This is going to be the flow of our talk throughout the presentation, as you can see from the slide. Next. Yeah. Lava tubes. Lava tubes is considered one of the most potential locations to construct a lunar base at the moon. Because of its ability to shield radiation and protect the astronauts from adverse temperatures. But there's minimum data which we have from Apollo missions which were conducted around for 50 years ago, and the satellite data which we have right now shows that the structural integrity of the lava tubes cannot be predicted, which poses a very high risk to collapsing due to moonquakes, either from meteorite impact or because of the tidal forces from Earth. So as to tackle this problem, we tend to propose a simple solution. Next. So our solution approach is to create an early warning moonquake early warning detection system at the moon using a network of low cost seismometers. The solution approach is once the moonquake is detected, a signal is sent to the main base via radio transmission. Once the signal is received, the computation period starts, and the signal is processed. And if a major earthquake is detected, an early warning system is given to the astronauts, which gives them crucial seconds to save their life and evacuate and escape safely. So the solution structure is classified into four parts, mainly the data stage, the processing stage, decision stage, and the alert stage. Satyank will be explaining more about this next.
All right, so as you can see, this is the basic structure of our system. The first stage is the data stage, in which we acquire the raw data from the seismometer network, which is set up around the base. And then it is sent into the processing stage, which has two subparts. In that, the first part, we filter the data and remove any noise, any presence of noise. And then we calculate the magnitude of the moonquake and the location of the epicenter. Once this data is calculated, we send the expected values through a threshold check. If the value exceeds the threshold, we alert the system and signal the astronauts that the base is in danger. If not, they can just take precautionary measures inside the base. So if the base is in danger, then the alarm system is triggered, and then they will be told to follow the necessary safety protocols which we have developed and will show on the later slides. Next. Also, we have gone through a risk assessment addressing potential risks and threats. For example, a vehicle may malfunction and fail to operate, or maybe an astronaut is feeling sick or loss of communication, etc. And as you can see on the chart on the right, from probability scale and the impact scale of 1 to 10, 1 being very remote and weak, and 10 being very frequent and severe. You can just go through that for 5 seconds. Next.
Yeah, hi. Now talking about the technological requirement, this is more about the power requirements of one seismometer station. So we have collected the data from NASA's previous missions, such as InSight Over in the Mars mission for the seismometer power requirement, and the Odyssey mission for the transmitter requirements. The data collected from these highly accurate payloads, we found out that it will require a maximum of 5.9 watt and 12 watt respectively. So this would give us a power requirement of a mere 18 watts per hour. So I mean, for a three setup mask, it would require around like 51 watt, which is very low. If we plan to use the 12 seismometer setup, which as you can see over here, the power requirement would increase. Next slide. Yeah, Satyak will talk about the post-alert safety procedure.
So I think our post-alert safety procedure is very simple and self-explanatory. The first step being where the astronauts are alerted when the warning system activates. And the next step, the immediate step, would be to wear suits and gear up to exit the base. Before that, they can keep all the essentials in a container and then cautiously exit the base. Then they can board the lunar vehicles and safely maneuver to the safest and the nearest base location. And once they enter the base, they can wait for further instructions from the ISS. Next.
Cool. Talking about the implementation method, we have planned of two ways to implement this idea here on Earth and test out. First one, the method one is collecting based on the data collected from the Swiss Seismological Institute run by ETH Zurich. So here we do not plan to set up any of the seismometers by ourselves. We plan to use the real-time data which can be provided by the Seismological Institute to our project. Real-time data from seismograms around which are in close vicinity to the project location. The data can be fed into the system and see if the system works or not, and test the precision of the system. The cost of this entire system would be literally €0, as we have no plans of purchasing seismograms, installing seismograms at our project location. And another method is more independent. We plan to set up our own seismometers. As an initial step, we plan to set up a 3 seismometer triangular simple arrangement around the base to test out the idea. This would cost us anywhere around 3,000 euros. The cost estimate is based on the products which are available in Europe itself. And if you plan to use a 12 seismometer star network, a 2-layer hexagonal pattern network, it would cost us anywhere near 12,300 euros. This is the setup which has a maximum accuracy. Next. Every seismometer station we have talked about here, including the 3 setup and the 12 setup star network, will have basically 4 components. One is an extremely precise seismometer. Second one is a solar panel, probably a 100-watt solar panel, which would be enough to power the seismometer throughout the day. So 100 solar panel, a transmitter array, and a battery as a backup power source. As in the right side, you can see how our seismometer station would generally look like in real life. Next. Cost approximations. We have calculated the cost approximation, like how much it would cost us if we test out the idea here on Earth, not on the Moon or Mars. So we have included the cost approximations in the report which we have sent. We have included the cost of seismograms, setting up the seismograms, radio transmitter setup, solar panels, and even installation and miscellaneous costs over there in Switzerland. And it would, as discussed earlier, it would probably cost us for the entire 12 seismogram setup around 12,300 euros, which is quite close to the 10,000 euros mark, which we had initially thought about. Next. So these are the references which you can go through. Next. That our team members. Next. Does anybody have any questions? Audience, mentors.
Yeah, wonderful. Great job. So I'll just give you a little feedback for your team real quick. I just want to state that this is a very good presentation, and in general, you have captured almost all of the things that we would generally look for in a pitch or presentation for a call to proposals. You have your problem statement, your solution approach, your risk assessment, the procedure, and some post-mortem procedures and requirements. I think it's really, really great. But then,
thank you so much.
Of course, but then there's a technical detail that it will be raised, and that is, say we've
included all the technical details in the report which we have submitted, since we thought it will be too much information in a presentation. All the calculations and all are there in the report which we have already submitted.
Okay, good, that's great. Okay. But the challenge here is not regarding those technical details. It's a more of an implementation detail. So if we only have a 2-day or 5-day or 7-day analog mission, and we don't detect any earthquakes, then does it make sense for us to invest 1,200 euros in a project? This would be the detail.
Yeah, true. I agree. We have 2 ways to approach this. One is either using the method one, which would cost us nothing, just based on the data collected from the Seismological Institute. All we can do is we can feed in doctor data, basically data from previous earthquakes around Switzerland. We can feed into the system and test out the system's accuracy and precision. Does it detect a major earthquake before, well in advance, or does it give out fake alarms? we need not necessarily set up the 12,000 euro the system. We can just test out using basic. Our main goal is to develop a software, so we can test out the software using the doctor data or data from the previous earthquake.
Okay, so for if we had an actual, if say we wanted to use your project or your idea, and would you say it would be possible that we could emulate or simulate an earthquake? So we tell the
Sure. So
astronauts that it's been,
if we
and they
have
follow the
plans of
procedure?
if you have plans of setting up the seismometers and then simulating, we can use a very ancient method, common method of simulating earthquake, the shaking table experiment. We can test this out and see if it would work or not.
Or we can just like feed data or simulate it computationally and then see like how our system behaves.
Okay, wonderful. Thank you. Okay, do we have other questions from the mentors first?
Hi, yes, I have a question concerning your warning system. I was wondering if you thought already of what kind of warning would it be? Would it be like a noise, lightning, something with lights to alert the astronauts? Have you thought of this part?
Actually, yeah, like in a base, like we'd have alarms more, and even light. We'd like to use both actually, because if it's really dangerous, you want everyone to know then and there that something is going to happen. And if astronauts have like something in the space suits or the suits which they wear inside the base, perhaps even with that we can give like haptics or something like that, so they'll get to know immediately.
The alarm systems are quite extensively used in the International Space Station right now. So we could borrow our idea from them and use a similar type of alarm system for the base too.
Okay, perfect. Thank you very much.
Any other questions?
Any questions from the fellow students, participants as well? Okay, I'll just add another question then. Suppose that you have an astronaut that's on a EVA, or they're on a spacewalk, they're out in the field, something like this, right? They're out on the moon looking for stuff. How would you recommend notifying them, basically a warning or alerting them that there is a potential earthquake? And do you have any type of protocol that you want to design for them to take if they're in the field?
Yeah, sure. I think as we said earlier about the alarm system, it can be incorporated into a person's spacesuit, so that even if they're outside carrying out any EVA activities, then they can be notified immediately. I think a safe protocol for that would be to return to the base first immediately, so that they can catch up with the other astronauts. Because one of our potential risks was loss of an astronaut. So we don't want to leave the astronaut just because he was outside carrying out an experiment. So the first step would be to return to the base, and then the entire crew would escort to the safest base location using the vehicles.
Okay, understood. Thank you.
Yep.
I have a question. You said that the signal was sent to the astronauts way before the moonquake or earthquake. How long is that? Because we have a potential location that is underground and a 2 kilometers tunnel to go back to the surface. Is that long enough? The signal is received how long before the
so like every earthquake or a moonquake has two parts, S wave and a P wave. So the P wave is a faster moving waves which first reach the seismometers. So they can detect, based on that we can calculate the magnitude and the destructiveness of the more stronger and powerful S waves. So once the SP waves have a speed around like 2 to 3 kilometers or a maximum 5 kilometers per hour, S wave is very low, somewhere around like 1 to 2 kilometers per hour. So once the P wave reaches the seismometer stations, the data will be instantly transmitted via radio. So that's the speed of light to the station. The computational speeds of the systems are extremely high in the present generation. So it would probably, based on the the location of the epicenter and all that, it will give us at least something like a minute or 2 minutes of minimum of 1 minute or 2 minutes of buffer time for the astronauts to evacuate.
Okay, thank you.
Sure.